Okay, this is going to take you through P1, which was all about different ways we can transfer energy, and then the second half of the module was looking at those electromagnetic waves and their uses. So the first bit of this topic actually just involves learning those two definitions. So you need to know the definition of heat and the definition of temperature. So if you remember, when we're talking about heat, we're talking about an actual measure of the amount of energy that's involved here. So because we're talking about energy, then that will always have the units joule, which is capital J. If, however, we're talking about temperature, then that's basically measuring how hot something is. Now, this has its own scale, whether it's degrees Celsius, degrees Fahrenheit, and what we're actually doing here is we're having a look to see how much kinetic energy there is in a substance. So hopefully you remember from various other topics that we've done that any time we actually make a substance hotter, basically what we're doing is giving those particles more kinetic energy. Now, the importance in terms of temperature and two different objects. If we think about, say, the example of a hot cup of tea in quite a cool room, then what we have there is quite a large difference in temperature between the coffee and the room itself. Now, because of that, what we actually have is this transfer of energy between those two things. So what we actually see is that the energy is going to go from the coffee, which is the hotter object, to the surroundings, which is the colder object. And that will always be the case. Energy will only ever move from the hot object to the cooler one. Okay. Now, the only other thing to make note of here is that this will happen at a much faster rate when there is a greater difference between those two temperatures. So if we've got a very dramatic difference between the two, we see it happening much quicker than if those two temperatures are very similar to one another. Now we come on to our first calculation of the topic. Now this is all about the specific heat capacity. Now what we actually have is the definition of this first of all, which is the amount of energy that is needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius. So what we'll actually find is that different substances have these different values for the specific heat capacity. Now that's not something you ever need to remember, because on your exam they will actually give you most likely a table with the different materials and their specific heat capacities for you to use in the question. Okay. Now what we actually do is on page 2 of the exam booklet, as always with all these calculations, you will find that equation listed at the bottom here. Okay. So to work out the amount of energy we need, it is going to be the mass of the substance, which is always in kilograms, multiplied by that specific heat capacity, which you'll get from the table, and the last bit is we multiply it by the temperature change. Now do go careful here, because the questions could very well say something along the lines of a substance starts at 20 degrees Celsius and it's going to be heated up to 80 degrees Celsius. So in that instance, obviously, we're looking for a temperature change, and in this case it will be the difference between 20 and 80, so our temperature change will be 60. So do just go careful when you're doing this calculation to make sure you work out that temperature change first of all. Now, in terms of the applications of this specific heat capacity, we'll see it in things like central heating systems. Now, they're all filled with water, because what we actually find is water has this specific heat capacity of 4,200. Now, that means it's going to gain an awful lot of energy to actually warm that up. Now, the big advantage of that is as that water then travels around the central heating system within the house, then it's got a lot of energy stored inside it that can then be transferred to the surroundings. Therefore, meaning you've got a very efficient heating system. Second calculation topic is the specific latent heat. Again, you will find the equation listed at the bottom of the slide on page 2 of your exam booklet, so you don't have to memorise it. Now, whenever we're talking about the specific latent heat to something, what we're talking about is the energy needed to change the state of it. So change it from a solid to a liquid to a gas, gas to liquid, or liquid to solid. So the amount of energy we need to do that is the specific latent heat. Now, what you'll actually find is they'll give you again one of those tables in the question, should they ask you to calculate this, where you'll have different materials in the first column, and then there will be 2 columns with numbers in following that. The first one is going to be most likely the specific latent heat of melting, or they sometimes call it the specific latent heat of fusion. Now, what that's referring to is the amount of energy needed to melt 1 kilogram of a material. So what we're actually doing in this instance is we're changing it from a solid to a liquid. Now, an important point to note here is that if they're asking you to change it from a liquid to a solid, then it's the exact same value, okay? So when you go from solid to liquid, it requires the same amount of energy as going from a liquid to a solid. The last column on that table will be the specific latent heat of boiling, or sometimes called the specific latent heat of vaporization. Now, that is going from liquid to gas. And again, it's changing 1 kilogram of that material. Okay? So all we need to do to actually calculate the amount of energy we need to actually do this, it will be the mass of the substance. Once more, remember, it will be in kilograms. And then you multiply it by the correct specific latent heat. So that requires you looking at the table, finding the right material, and then what you need to do is obviously remember whether it's going from solid to liquid or liquid to gas, and pick the right column there. Multiply those two together, and then you get your amount of energy required. Next little bit then is looking at these graphs. Now these are both heating and cooling curves. Heating curve on the left, cooling curve on the right. Now, the actual shape of these is very distinctive, because what we can see here is that not all times will the temperature change. So if you have a look at the heating on the left first of all, what we can see is our temperature starts off very low, and then what we actually see is an increase in temperature. So that diagonal line sloping up means the temperature of our solid is increasing. Now it will keep doing that until it gets to a certain temperature where you can see it begins to level off and it forms that plateau. Now at this point what we see is our solid is melting. Now we don't see an increase in temperature at this point because all of that energy we're putting into it by applying heat, that is going in to break those intermolecular bonds. So obviously in our solid what we have are those particles held in this very distinctive structure by intermolecular bonds, and it requires energy to break them. So all the time that we're actually breaking the bonds between the particles in our solid, then the temperature does not increase. As soon as we've broken all those bonds and all of those particles are now in liquid state, then the liquid warms up, which means the temperature will increase once more. Then obviously we hit another plateau, as we can see in the graph. That is down to the fact that we're now breaking the bonds between the particles in our liquid to change them into a gas. So finally, once all of that is as a gas, then the gas warms up, therefore the temperature will increase again. If we look at the cooling curve on the right, then it's basically the inverse is happening. Where we get those plateaus, it's where it is then forming into a liquid or forming into a solid once more. So the key thing to remember is wherever we have plateaus on either heating or cooling curves, all of the energy we're putting into that substance at a time is being used to either make or break intermolecular bonds. So do remember that fact, because it can sometimes be that 1-mark question asking why the temperature doesn't change at that particular point, and then all you need to do is say that all of the energy is going into either making or breaking bonds, whichever is relevant for that instance. Our first energy transfer then is looking at the process of conduction. Now, conduction is the one that happens mainly in solids. So this is what's happening, for example, when you did the experiment where you had the little drawing pin stuck onto the end of a metal rod with Vaseline and you heated the other end, then the drawing pin fell off. That was demonstrating conduction for you. So in your solid, hope you remember from year 7, then all of those particles are very neatly arranged in a nice orderly pattern, very close together. Now what happens is, as we start to heat up one end, those particles gain more energy, they start to vibrate more, and then as they knock into the particles next to them, they transfer the energy along. So basically what we end up doing is that kinetic energy is then passed from one particle to the next in a little chain. Now that's true of all of these materials, but when we consider metals, which are very good conductors of heat, then the reason for that is this thing called the free electrons. So what we have inside metals are these electrons that are free to move about inside the metal. So what happens there is those electrons gain the energy, and then because they're able to literally zip along amongst all of the actual metal atoms, then they're able to transfer the energy along that whole piece of metal much faster than if they were in a fixed location. So if it asks you why metals are very good conductors of heat, it's because of free electrons. So our second form of energy transfer then is convection. Now, convection can only take place in either liquids or gases. So this doesn't happen in solids. Now, what we actually find with convection then is as we heat up particles, then they move faster. So as those particles move faster, then the fluid, which is the liquid or the gas, expands. Now, as something expands and the particles become more spaced out, then they become less dense. So what this then means is that this warmer, less dense fluid is going to rise up, and therefore what we actually find is that's going to go up towards the top of whatever space we have, say the room. Now, at the same time, we're going to have energy being transferred from our actual fluid to something else. So that means our fluid actually cools down as well. So this is what we see, say, happening in our houses. So what happens is all of this warmer, less dense air is going to rise up. Energy is then transferred elsewhere, which means that our particles start to lose that energy. They move closer together again and become more dense. So as they become more dense, they're obviously going to sink back down. So what we end up generating are these things called convection currents. So all of the warmer, less dense fluid will rise, and then the cooler, more dense fluid sinks down. So we generate this current that then obviously keeps this cycle going. Now, if we actually wanted to find a way to reduce our convection, then what we need to do is stop the fluid from moving. So this is basically what we're doing when we put in things like loft insulation or cavity wall insulation. What we're doing is we're trapping those little particles of air and therefore preventing them from setting up these convection currents. So normally if we think about cavity wall, you've got this space between the two layers of brick, and then if we actually fill it with this foam, it's obviously going to trap the little particles of air in small bubbles. So that's going to stop it actually setting up this current which is able to flow from the sort of lower parts of your house right the way up to the roof space where we're going to lose a lot of energy. So by trapping our fluid, we reduce the amount of heat loss by convection. So our third and final way of actually transferring energy is radiation then. Now, when we're talking about radiation, we're talking about heat being transferred as these infrared waves. So basically what we've got here is our first version of electromagnetic waves, which we're going to come on to look at in the second half of this topic. Now, the key thing to remember about our waves is they do not need particles to travel. So unlike conduction and convection that rely on particles to allow the energy to be transferred from place to place, when we're talking about radiation, it requires no particles. So this is why the sun can heat up Earth through space, which has none of these particles present. Now, what we'll actually find though is one limitation is that it will only occur if we use transparent substances. Okay? Now, we do have the amount of radiation dependent on two particular aspects of our object. First one is the colour of the surface, and the second one is the texture. So what we actually find then is if we compare a matte black surface with a light and shiny surface, our matte black one will absorb more heat radiation than light and shiny surfaces. This is why you'll see houses in these very hot countries, they tend to be painted white. Because obviously what it's going to do there is it's going to reflect off more of that actual infrared radiation and therefore keep the inside of the house cooler. Whereas if we were to paint all of those houses a matte black colour, they'd absorb a lot more of the infrared radiation and therefore in that instance make it much hotter. The other one to bear in mind is when we're talking about radiation, if we've got a very hot object, it is going to be emitting a lot more infrared than a cooler object. So in terms of what we're actually going to use these things for, the first one is cooking. Okay. Now, what we actually find is if we're actually thinking about items in our kitchen, then the grill and the toaster, they heat our food up by using infrared radiation. Now, that's not why they glow red, remember, because infrared radiation is not visible to our eyes. but infrared radiation is the source of the energy to heat up the food, okay? So what we actually have then, if we consider our grill, for example, the heat is radiated from the grill itself, and it's absorbed by the particles that make up the surface of our food. Now, as they absorb that energy, then the kinetic energy of those particles will increase. So what we then see is they will pass that energy onto the other particles that they're in contact with by conduction or convection, depending on, obviously, we're talking about whether it's a solid or a liquid that we're heating up in this instance. But do remember that the only way the central parts can actually be heated up in our food is through the conduction or convection transferring it from the outermost particles. Microwaves then, slightly different way of heating up our food here. They're going to use microwave radiation, as the name suggests. Okay, hopefully you would get that mark on the exam paper. Now, one thing to note about our microwaves then is that they're able to penetrate about 1 centimetre into the food. Now, where they do that, then they're going to be absorbed by fat or water particles inside our food. And again, what we then see is from that point, conduction or convection will then transfer the energy further into the food. So the processes are actually quite similar in the way that particles absorb the energy first of all, and then it's passed on through conduction and convection. One difference to note though is the microwaves are able to penetrate 1 centimetre in, whereas our normal infrared radiation, it's literally just the very surface that actually has the radiation being absorbed. So, saving energy came next. Obviously we've talked about ways that our energy can actually be lost from items. So now we actually need to understand how we could try to save some of this energy. Now, a couple of key words first of all. If we're talking about a source, then they are the ones that are emitting the radiation, whereas a sink is the one that's going to have the energy being transferred to it and therefore energy being lost from it. Okay? So what we can actually do in terms of ways we can save energy, it's insulation or it's improving the efficiency of the items involved. So what we actually will have here most likely in your exam is a question about different types of insulations. Okay? Now, one thing to bear in mind is while most of the equations for physics are on page 2 of your exam booklet, this one here, the payback time, is not. So you do have to learn the equation for payback time. It's quite a simple one. Okay? All you need to do is take the initial cost for installing that type of insulation and divide it by your annual saving. So that then gives you the number of years it will actually take to have made that money back, okay, hence payback time. Now what you can obviously do there is you can compare different types of insulation for their cost effectiveness. The one with the shortest payback time will be the best insulation to put in, because it means you've got the shortest period of time from putting it in to having saved that same amount of money as it cost you to put in the first place. So do go careful with this one, and obviously, as with all calculations, show your working should you actually have to use the calculations. So one way we can actually identify where energy is being lost is by using this idea of a special picture called a thermogram. Now what we can actually do is if we have a house that we want to know obviously where the actual heat energy is being lost from, then what we can actually do is use this special camera, take the image, the thermogram, and then by looking to see what colours are shown on which different parts of the house, we can work out where we're losing the most heat. So what we find is those bits that show up as white, yellow or red, they're losing the most heat. So generally speaking, it'll be things like the windows, maybe the roof if we've not got any loft insulation in. Whereas the bits that are very cold, therefore the ones that aren't losing much heat, they're the black, the blue and the purple coloured ones. So what we'll see here is just at a glance, you can identify where heat energy is being lost from an object. And therefore, obviously, that will give you the opportunity to make informed decisions about what the best type of insulation to use would be. Right, energy efficiency comes next. Now, again, does have a calculation here, but it is in your exam booklets, okay? Now, one thing to note is the difference in our types of energy here. You obviously have the useful energy, which is actually the energy we're using for the specified task. So if we're talking about a lamp, the useful energy would be light energy, because we're using the actual lamp to provide light. whereas the wasted energy is anything else that we're producing that's not being used for that task. So going back to our example of the lamp, this would be the heat that's also generated by the bulb. It's not useful, so therefore it is wasted energy. Now, to calculate the efficiency, we always give this as a percentage, okay? So the first thing we're going to do is we're going to divide the useful energy output by the total energy input. And then we multiply that by 100 to give it as a percentage. The only other type of question they could ask you here on your exam is one of these Sankey diagrams, which, if you remember from our lessons, they show basically an arrow that then splits into the different types of energy we're making. So what we actually have there is they have in the past given you a small section of graph paper and asked you to draw it to scale. Now, they may give you the scale in the question. If not, then obviously pick a logical scale here. It's not going to be overly complex for you. So all you need to do is make sure that the width of the arrow is the same as the amount of the energy. So if, for example, you had 100 joules being put into our particular example, then you might choose to do it 10 centimeters tall, and then sort of say that 10 joules is the same as 1 centimeter in your diagram. Okay, just remember to use that throughout when drawing your Sankey diagram and label on those different energies, so light energy, heat energy, and so forth. Right, second part of this topic was all about waves. Now, what we have here is a diagram you should remember with those key parts labelled on. So what we can actually see on our diagram then, first point to note is the highest point of those waves are called peaks. The lowest point of our wave is called a trough. So what we actually have there are the highest and lowest points labelled on. Do remember those two terms because they have asked you to label it before. The other ones we've got on there are wavelength and amplitude. Now the amplitude, first of all, if you look at the diagram, you can see that goes from the middle line, which is where our wave would be at rest, up to the highest point of a peak, or if you're going down, the lowest point in our trough. So it's literally the height of the wave, okay? Now the other one we've got labelled on the diagram, that red arrow at the top, shows you what is a wavelength. Now quite simply, that is the distance between two peaks, or again we can do this underneath, and it's the distance between two troughs. So that is the equivalent of one wavelength, and that's always measured in meters. The only other term we need to remember in terms of our waves is this thing called frequency, which quite simply is the number of complete cycles per second. Now that's measured in these units called hertz. So what we actually find then is that one of those waves that has a higher frequency has a lot more waves packed in on the diagram. So what you'll see is they'll be very squashed together with a high frequency wave, whereas if it's a low frequency wave, it'll be far more spread out. Now, there is a calculation associated with this, which again, you find on page 2 of your exam booklet, which is all to do with calculating the speed of our wave. Now, quite simple here, all we do is the frequency multiplied by the wavelength. Now, obviously those of you doing the higher tier paper, you could be asked to rearrange this equation, in which case, just use your triangle method. So what we'll have is on the top would be speed, and the bottom would be your frequency and the wavelength. Then obviously just by covering up the one you want, you get your actual calculation for whatever one they happen to ask you from the three. So wave behaviour comes next. Now one thing to remember is whatever wave we're talking about, any wave at all, can be reflected, refracted and diffracted. So those three things will happen to any wave at all. So if we take our first one, the reflection first of all. Now one thing you should remember from the lower school is that the angle of incidence, that is the angle at which our wave comes in at, is going to be exactly the same as the angle of reflection. Think about where we've done experiments with light against an actual mirror. The angle it comes in at, it gets reflected off at that same angle. So do go careful with that one. Now one thing we went on to extend that to was this idea of total internal reflection. Now this is where all of our light is actually being reflected inside an object. Now to actually have total internal reflection taking place, we've got to make sure that the angle at which our light is coming in at is greater than the critical angle of our substance. So what we actually see, we've got three diagrams at the bottom there. So our first one is showing you how total internal reflection will occur, because the bit in red is the critical angle, and we can see that our angle of incidence is greater than that. Therefore, all light will be reflected inside our object. The middle diagram, we can see that our angle of incidence is actually smaller than our critical angle, which means most of it actually passes out. Okay, so what we will see there is that we lose most of our energy. The last one is where our actual angle of incidence is exactly the same as our critical angle, and in this instance it's actually going to travel straight away along the boundary. So our next bit then is looking at the other two ways in which our waves behave. Refraction, first of all, and now this is going to occur where we've got our wave travelling through two different mediums. So we could have something like our light passing through plastic, then air. Okay. Now what we find is, because those mediums have different densities, then our wave is able to travel at different speeds. So what we find is the less dense the medium, the faster the wave can travel. So what we see there is, as soon as our actual wave is going to hit at an angle on that boundary, then obviously one side of the wave is going to start travelling at a different speed before the rest. So that basically means our wave will start to bend. So that is what refraction is. It's the bending of our light. Now diffraction then is actually just defined as the spreading out of our waves. So if we actually pass a wave through a small gap, then on the other side what we actually see is those waves then begin to spread out again. Now key thing to note here is, if we've got a narrow gap or a long wavelength, then we see a greater amount of diffraction occurring. Right, the electromagnetic spectrum, you need to know this in order. They usually have a nice question where you can pick up some marks just for filling in the missing spaces, basically. So what we actually have are 7 different electromagnetic waves. So we start off with radio waves, then it's microwaves, infrared, visible light in the middle, and then we come on to the ultraviolet, the X-rays, and the gamma rays. Just learn those waves in the correct order. They will always give you some in the sequence, then all you do is you fit in the missing ones in the empty spaces. That should be nice easy marks for you on the exam. Now what we tend to find then is, if we're talking about waves with higher frequencies, then they have more energy. Now that does make them more dangerous as a wave. What we see happening is, if you absorb these electromagnetic waves, then you have heating and ionization. And if you remember, when we talked about ionization before, this is the gain or loss of electrons from a particular substance. Now one other thing to note about our electromagnetic spectrum and the waves that make it up is that those at the ends of our spectrum tend to pass through objects, whereas it's those in the middle that are going to be absorbed. So that's where we start to see those problems with things like the infrared and the ultraviolet, because if you look at the spectrum, they're the ones in the middle, okay? So they're the ones that will be absorbed by our skin and therefore lead to the problems. So the next bit we came on to look at was comparing different types of signals that we can actually have. So if we have a look at things like light and radio and electrical signals, they're all very fast signals. Now what we can actually do is, by using things like electrical wires and optic fibres, we can transmit a large amount of information. So this is why things like broadband these days tends to be fibre optic, for those really high speed ones. Now the other big advantage is that if we're transferring information via optic fibres or electrical cables, then it's actually very secure, because the only way you can access that information is by physically breaking into that cable. But the downside, because all of these things do have a downside, is that should there be a problem with our cable, it's quite difficult to repair, because a lot of the time these cables are buried underground, so that requires digging up the roads or pavements in order to actually carry out those repairs. If we actually compare that to our wireless communication, then obviously we do have the big advantage with wireless of it being completely portable. You can take it anywhere you like. However, there is obviously the limitation of how strong your signal is. You all know that if you've tried accessing things on your phone and so on, it's down to the signal strength whether it works or not. Exactly the same idea with all wireless communication. You've got to have a strong enough signal for it to work. So light was one of our first ways of communicating. And what we actually need to use light as a form of communication is a code. And what we use is Morse code. So what we actually have with Morse code is a version of a digital signal because it's on or it's off. Now, the big advantage of this is we're actually allowed to communicate over very long distances very quickly. So it was obviously used an awful lot of time before, obviously mobile phones and everything like this. So we could actually send information large distances along sort of either sea or land just by sending signals which were flashes of light. So here we see our total internal reflection in use. Now we're using these substances called optic fibers. Now we can send information through these optic fibers either as pulses of light or as this infrared radiation. Now one great thing about them is, we've already said it's very fast, but another thing we can do is what's called multiplexing. Now multiplexing quite simply is a way of sending more than one set of information at the same time. We can stack signals up on top of each other because of its digital nature. So what we actually do here is, as we can see in the diagram, we have two light signals being sent down the same optic fiber at the same time. Now that has the big advantage of allowing us to transmit larger amounts of information in the same period of time. So in terms of what we're actually going to use this for, we'll use it for telephone and broadband cables these days. We can use it in artificial Christmas trees. And we can also use it in this thing called an endoscope, which is a bit of medical equipment that allows us to obviously view inside the body without having to do any kind of invasive surgery. So we can literally pass the camera down the throat and then view what's going inside the body without having to cut anyone open at all. So what we see in terms of the advantages then, number one, it's very quick. Number two, we've got this multiplexing where we're sending lots of signals along one optic fiber at the same time. And because we're talking about digital signals, we're not getting much interference here. Okay, so we get a much better quality of signal. So lasers are the next bit. Now, a couple of key words here. Okay, when we're talking about something being monochromatic, we mean it is one color. So what we see with our lasers is that they tend to be one color of light. So obviously they do occur in different colours. You can have red lasers, blue lasers, green lasers, but they are all monochromatic. Okay. Now the other one here is that we have this word called divergence, which is to do with it spreading out. Now when we look at a laser, its big advantage is that it had this low divergence. So that means that it will stay nice and closely packed together, so it doesn't spread out, even over long distances. So when we're thinking about these laser light shows and things like this that they can put on, they're kept in a very narrow beam, which makes it obviously much clearer in terms of its display. So what we actually end up with then is this one coloured light, okay, which is having a very low divergence, and the other thing that they might say is that they're in phase. Now that just means that all of those little wavelengths stack up perfectly on top of one another. And the reason for that is that they are monochromatic. They're all one colour. Okay, so they're all the same frequency, all the same wavelength, hence them being in phase with one another. And they've got a low divergence, which means they don't spread out. So do remember those three key words of monochromatic, in phase, and also divergence. Now, in terms of what we'd actually use a laser for, the one you need to remember for your exam is talking about CD players. Now, what we actually have, our CD itself has these tiny little microscopic pits cut into it. So between those pits, we've got these flat bits called lags. Now, what happens is, as our CD is spinning inside our player, then we've got a little laser that's shining up onto its surface. Now, what happens is, that laser is going to be reflected off the surface of the CD because it's so shiny. Now, what we have built into our device is this light sensor that then detects those different reflections. Now, what we'll see is, you're going to get a reflection that is very different from a land and a pit. So basically, what we're generating are a series of flashes. That's a series of pulses that we get. So it's kind of like going back to our Morse code. And all that happens then is our device is then clever enough to convert that into electrical signals, which are then changed into sound by our amplifier and loudspeaker. So what we see, first of all, is we get the reflections of the actual laser itself. It's detected by a light sensor. It's converted to electrical signals, and those electrical signals are then changed into sound. Infrared is another very important type of electromagnetic wave for us. We use it every day in our remote controls. So what we're actually doing there is sending these little pulses of infrared as a digital code once more to our TV, our hi-fi, whatever it is we're using. Now, there are a couple of things that we do have to bear in mind with our remote controls. You've got to be within a certain distance, you can't be a long distance away, and you've also got to point them directly at the detector, because we are talking about waves and they travel in straight lines only. Okay, so do bear that in mind for the disadvantages, so to speak. We'll also use infrared, as we've already looked at earlier, in cooking, and a couple of other ones we can use it for. Security systems, we'll actually use infrared sensors, and we can monitor the temperature, because as we said back at the beginning of this topic, when we have a hot object, it gives out more infrared radiation than a cold object. Now, in terms of wireless communication, then what we actually find is that radio waves and microwaves are very good at transferring information over long distances. Now, the reason for that is because, as we said earlier on, they are towards the ends of our actual electromagnetic spectrum, which means that they're not absorbed. Okay, they pass through objects. Now, one big downside though is that should our waves start to diffract, then our signal will get weaker. So if we've had a large amount of diffraction, then the signal gets weak very quickly. So if we think about radio waves then, basically they're split up into different categories, if you will. We've got our long wave radio waves, and they are between 1 and 10 kilometers in length, okay, so very large waves here. Now, these can be transmitted over long distances because they're actually able to diffract around the Earth's curved surface, okay. Now, if we compare that to our short wavelengths, such as our TV and FM radio signals here, they've only got a wavelength of between 10 centimeters and 10 meters, so they're much smaller here. And they can only be used when we've got this line of sight between the transmitter, okay? Because these ones, they're shorter and they don't diffract as well. Which, remember what we said earlier on, longer wavelengths show greater diffraction. So our shorter wavelengths show less diffraction. Now, if we're talking about our shortwave radio signals, the ones between 10 meters and 100 meters, these ones actually use that charged part of our atmosphere, the ionosphere, to actually reflect those radio signals. So this allows them to travel a bit further than they would be able to do otherwise. Now, if we actually think about our ionosphere then, as I said, this is the electrically charged part of our atmosphere. So what we see happening here is, if we think about our radio waves, they're able to travel faster through ionized parts than the non-ionized parts. So we see refraction taking place, because it's just like going through different densities. As those waves move through, obviously, the ionized parts, then they're able to travel faster. As soon as they hit the boundary between the non-ionized part, then it's going to slow down there. So what we see is refraction taking place. Now, the next bit that we're going to see is our short and medium wave radio signals will refract the most. This means they're able to travel further. So 3 things to remember, okay, when we're talking about diffraction. First thing is that it depends upon the frequency and the angle of elevation. So remember those 2 things that actually affect the amount of diffraction that will occur. So what we actually see is, if we've got a low frequency and angle of elevation, then they're going to refract back to the Earth nice and quickly. Okay, so remember that pattern. What we have these days then is digital radio. Now, when we compare digital and analog radio, then what we see is our digital has less interference. Okay. Now, what we actually have in addition to that is we've got a lot more stations available on our digital radios than on the old analog. So there are 2 big advantages of digital radio. Okay. However, there is a downside to it, in that we can have a lower sound quality due to the fact that those signals are actually being compressed. So when you squash down a sound file, you do lose some of the quality. Okay. Now, again, remember what we can have is this multiplexing idea, because we can send more than one signal along that same frequency, which means that we can then have a greater number of stations. Okay. But we do need a digital radio to do this, okay, or a DAB radio. Now, microwaves aren't just used for cooking. Okay, microwaves are also used in a number of different communications. So things like satellite communication and mobile phones all use microwaves. So what we actually have then is they are going to be transmitted from Earth and sent up into space. When it gets there, there will be a satellite that will reflect those microwaves back, and it will be received by a satellite dish on the ground. Now, these do have a shorter wavelength than our radio waves, so what we tend to find is that they don't diffract, and if you've got a large obstacle in the way, then it blocks that signal. So this is why your mobile phones don't work absolutely everywhere, okay, because they do use this microwave communication. Now, one of the questions they do like to ask is, what are the possible risks of mobile phones? Now, because we're talking about microwave radiation, then what we can see is that cells may be burned, that they may be killed, possibly the risk of tumours, but the key thing to remember is that we don't actually have any definitive proof yet. So this is the key thing, is that yes, there are some scientific studies that have said, oh look, we've got this link, but then there are also other ones that say, actually, no, there isn't a link. So do remember the fact that because we have no definitive proof, then these are just theories at this point in time. But the key thing to remember is obviously it can lead to cancer, it can lead to damage of cells, okay? Anything along those lines you're going to get marks for in the exam paper. So in terms of the electromagnetic receivers that we need to actually use these electromagnetic waves, then first thing to note is that the minimum size the receiver can be is linked into the size of the wavelength it's trying to actually receive. So what we actually find is that some of these wavelengths are incredibly large, so what we actually need is a very, very big receiver. Now if we think about these telescopes that we've got, is bigger ones are better, okay? Because what we have is a better resolution because there's less diffraction taking place. Now, if we think about radio telescopes, then what we tend to do is we link a large number of them together to provide more detailed information. Because if we actually think about the size that one radio telescope would have to be, or the size of one of those radio waves, it's not actually feasible to do it, okay? So what we have to do there is use a number of smaller radio telescopes all linked together to provide better information, because we couldn't have just one that actually matched the wavelength, because it would be just too physically large. So if we come in to compare our analog and our digital signals then, when we're talking about analog, we're talking about something that could be anything within a range of values. So what we see is that the amplitude and the frequency are varying constantly. Now, as a result of this, it's far more prone to interference, or what's called noise. Now, when we see one of these as a diagram, what it'll actually be is kind of like a wave. Okay, so like we've seen with the waves, but uneven. Okay, so that'll be our analog signal. If we're looking at a digital signal, then it only has two values. It's either on or it's off. So because of that, we've obviously got a lot less interference, because if it doesn't fit the on or off category, it's not meant to be there and it can be removed. The other one to bear in mind is with all these digital signals, we can do multiplexing, so send more than one signal at that same time to transmit a greater amount of information. So if we see a diagram of a digital signal, it's literally going to be a series of rectangles on a page. So the last bit of this topic was just looking to see about humans and the environment. Now, one thing that happens is ultraviolet, okay, this is the cause of skin cancer. The way it does it is it's absorbed by the cells in our skin. That is then going to lead to our DNA being ionized or damaged, and this is then going to lead to the potential risk of mutations. That then means our cells could divide uncontrollably, leading to tumours. Okay, so that's our skin cancer. Now, what we can do to try to avoid these risks is obviously use sun creams. Now, when we're talking about sun creams, they all have that SPF number on them, sun protection factor. Now that tells you how much longer you can actually stay out in the sun before you start to burn, okay? So obviously the higher the SPF, the longer you're able to stay in the sun before burning. Now the other bit that we've actually got is we've got natural protection built in on our planet, which is the ozone layer. Now the ozone layer actually protects us from a lot of harmful ultraviolet radiation. The downside though is as humans, what we created these chemicals called CFCs. Now, when we used a lot of CFCs, which were in things like aerosol cans, fridges and so on, then as they were released into our atmosphere, they've led to parts of our ozone layer becoming much thinner. Now that obviously means that if the ozone layer is thinner, more ultraviolet radiation can reach the surface of the Earth, which obviously is bad news for us, because that means we're exposed to more ultraviolet radiation. So the very last bit of this topic was seismic waves. So first point to note is they're caused by earthquakes. So where we have an earthquake occurring, we're making these two types of seismic waves, the S waves and the P waves. Now you should remember these few key things about those two types of waves. So if we take our S waves first of all, they are what's called a transverse wave, and they only travel through solids. So think S and solid. And the other one is they're very slow. So with what we've got with our S waves are solids and slow, so all those S's together. If we look at the P waves on the alternative side, they are longitudinal waves first of all. They can travel through both solids and liquids, and they're much quicker than our S waves. So what we have here is a comparison between those two types of wave, and as we saw in our chemistry topic, this is how we've learnt about the structure of the Earth, just by studying where we get S waves and where we get P waves. And obviously using that information, the S waves only travel through a solid, whereas our P waves travel through both solids and liquids. So that summarises all of P1 for you. Hope that that's nice and clear, and obviously if you do have any questions, then ask before your exam.